In the second video, we will also look at selection weights, but this time we're going to demonstrate how we can do conditional routing. So in the previous example that we did, we said 80% pass and 20% fail, and so that was a random choice. And for this video, what we want to do is look at a conditional choice. So in particular, what we want to consider is the case where any given TV can go through a maximum of 3 adjustments. So if the TV is adjusted for the 4th time or fails inspection after the 3rd adjustment, then we want to remove the TV from the system and reject it. So we will start with the model that we ended with in the previous video. So here's the model where we have our source, our adjust, and our inspect. And we have this probabilistic routing, 80% pass and 20% fail. And so what we want to do is add this idea of a conditional routing. And so when we see our condition, the maximum of 3 adjustments for a given TV, that lets us know that we need to somehow record or count the number of adjustments for each individual TV. So now we have a probabilistic, any TV goes through inspection and it probabilistically gets routed back, but we don't track that in any way. So the first step for our modified model is to record the number of times that each individual TV is adjusted. So to do that, we have a two-step process. We need to define a model entity state where we record the value, and then we need to use a state assignment to actually adjust or actually update the model entity state. So I'm going to go to Model Entity, Definitions, and create a state. I need an integer state that I'm going to name num adjust. And so I've created a state associated with an entity. It has an initial value of 0. So that's the first step, creating the location to store the value. The second step is to do the actual state assignment. So when a realization of the TV instance goes through the adjustment process, we want to increment that value. So I'm going to click on adjust and use the state assignment, and I want to, before exiting, make a state assignment to increment that value. So the value that I want is model entity num adjust, there it is, and I want to increment that value, so I'll just do model entity num adjust plus 1. So when the entity departs adjustment, the adjustment process, I will add 1 to the previous value of num adjust. And so now when the entity departs, it should have the number of times that the entity has been adjusted. So to see that and to verify that that's actually happening, what I would like to do before we add the condition is add a tally statistic to record the value when the entities leave the sink. So in other words, what I want to do is when an entity departs, right here, I want to record the corresponding value in the num adjust state so that I can observe those values. So to do that, I'm going to go to Model, Definitions, Elements, and create what's called a tally statistic. And the tally statistic I'm going to do is number of adjustments. And so this tells Simio that I want to create a tally statistic, and I'm going to then record observations at some point in my model. So the next step in our tally statistic is to record the actual observations. And so I'm going to use the tally statistics property right here on the input to sync 1. So if I expand that box, when an entity enters the input node, I'm going to record that value. So I'll open the repeat editor and add my tally statistic, and so I can select my tallies, and so I have number of adjustments, the one I just created, and I'd like to record an expression, and the expression value I want to record is simply model entity num adjust. And so what this says is when an entity enters the input node for sync 1, I want to record that entity's value of num adjust in the semio tally statistic num adjustments. And so if we just do a little quick run in interactive mode here, we can see when we look at the results, we now have a new category of user-specified statistics, and we see the average, maximum, and the number of observations. Similarly, we can update our experiment so that we can add responses. And so I'm going to add response for the average number of adjusts. I'll just call it AVNA. And so I look at adjustments, number of adjustments, average. So the average number of adjustments. And let's also look at the maximum number of adjustments. So we'll just call this max NA for maximum number of adjustments. And we will select maximum. So maximum number of adjustments. And so now we've added our two responses for our experiment. So I reset because I've added my new responses, and I will go ahead and run my experiment. And we can now look at our responses, so average number of adjustments, maximum number of adjustments. And for our two scenarios, recall the difference between the scenarios was the distribution of processing times at adjustment. And as we would expect, or as I hope we would expect, the number of adjustments, both average and maximum, shouldn't be different between these two scenarios because all we're changing is the processing time distribution. So we see that. We can look at these values also and say, again, is this in line with what we expect? And if we go back to our static model, we can use the computed value for what we called split, and we see that these number should be equivalent to the split. So this is 1.25 or 125%, and that's in fact what we see here. So we would expect the TVs to be adjusted on average 1.25 times, and that is in line with what we're seeing in our experiment. So we're satisfied now that we have correctly captured the value of the number of adjustments here. And so the next phase is to make the conditional decision here that says if the entity has been adjusted more than 3 times, we want to reject it. Before we put the condition in though, let's adjust the symbols so that we can use the color of the entity in the animation to indicate the number of times that an individual TV has been adjusted. So what I'm going to do is I'm going to go to my TV instance and add additional symbols, and I want to have 5 symbols corresponding to 0 through 4 adjustments, and I'll change the color for each one. So if it's been adjusted 1 time, it will be red. Adjusted 2 times, it'll be dark blue. Adjusted 3 times, let's make it purple. And finally, if it's been adjusted 4 times, we'll make it black. And so we have now a symbol list for our symbol instance for model entity. When we have previously used the symbol list, what we did was a second step is we incremented or we updated the model entity.picture state so that when an appropriate change in state occurred. This time instead, what we're going to do is we're going to use the current symbol index property, where previously that's been set to model entity.picture. Now we're simply going to have the value of model entity num adjust. So our entity state that we've created to indicate the which symbol from the symbol list to use. And so now when we run the model, we're going to see the entities, once they depart adjust, they turn red, corresponding to incrementing that value, which we have already done here. If entities come all the way around, so if they fail, like the one we just saw, we'll see red entities here in the adjust queue. So we have a potential problem in our model here, and if we run in fast forward mode, perhaps we'll see it. Nope, we're not going to see it in fast forward mode because the animation is off. Maybe we can see it if we increase the run speed a little bit. So let's let it run for a little while. Let's increase it a little bit more. See if we can make this error happen. So we'll let it run. And maybe it's not going to happen. And finally, here we are at time 23.45. And what we see is that we get an error saying the symbol index 5 for object TV is out of the range 0 to 4. So what's happening is we use the entity state of num_adjust as an index into the symbol range, but we only defined 5 symbols from 0 to 4. And so when the first TV was rejected for the 4th time, we tried to increase that value and we were out of the symbol range. So we could fix this a couple of different ways. One way we could do it is we could just add additional symbols. But since we don't really know how many times that the entity can fail, a TV can fail, and in fact theoretically it could fail an infinite number of times, we're going to use the current symbol index and make a little adjustment. What we're going to do is we're going to use math if and use a condition on the number of adjustments. So if the number of adjusts is less than 4, we're going to use model entity num_adjust as the index. Otherwise, we'll simply use the index 4. So what our condition now says, or what our property now says, is if the model entity number of adjusts is less than 4, in other words, if it's been adjusted 0, 1, 2, or 3 times, we will use that as an index into the symbol list. Otherwise, we'll just use a static value of 4, so the 4th index. So now what happens when we run is we should see no difference until we get to that time 23 where the error occurred. So let me increase this even further, see if we can get there a little more quickly. So here we are at 12 hours, 14, 17, 19, and now when we get to where we failed before, we continue processing. Because we reach that alternative if condition where the number was not less than 4, and so we just assigned the fixed value of 4 to the index and solved our problem. So now back to our problem at hand at rejecting TVs that have been adjusted more than 3 times. And so in essence what we need to do at this decision point right here, instead of a probabilistic decision of 80-20, I also want a condition that if the TV has been adjusted more than 3 times, I want to reject. So what I'm going to do is add another sink here and add a 3rd path from our inspect right here. And I'm going to rename these guys good. This is our good exit, and this is our bad exit. And so now we have an alternative, and if we just run right now, what we would see is we have a selection weight of 20 here, a selection weight of 80 here, and a selection weight of 1 here. And so we have just applied a probabilistic routing, which is not what we want. So instead, what I'm going to do is add a condition on the selection weight. In particular, I'm going to set the selection weight for the bad path to be model entity num_adjust equals 4. And note that I used the equal here, signifying that I am checking for equality between the num_adjust entity state and the value of 4. And so instead of having a probability, I'm having an expression that will resolve to either a value of 0 or 1. So if the entity has a state num_adjust equal to 4, then this path selection weight will resolve to 1. Otherwise, if it's 0, 1, 2, 3, or anything other than 4, the selection weight will resolve to 0. So I also need to make a small modification to our other 2 selection weights, and so I'm going to do 80 times model entity num adjusts less than 4. So the condition now says 80 times model entity dot num adjust less than 4, and so this model entity dot num adjust less than 4 will resolve to either 0 or 1. If num adjust is less than 4, the parenthetical condition will resolve to 1, and the link weight will resolve to 80. So I need to do the same thing for our additional branch, our additional link. So I'm going to now do 20 times the same condition, model entity num adjusts less than 4. And so now what's going to happen is if num adjusts is less than 4, these two path, the link weights will resolve to 80 and 20 respectively, and the third one will resolve to 0. And we will make the probabilistic branch between good and adjust. In the case where an entity arrives and num adjust is equal to 4, then these two paths will resolve to 0, and the bad path will resolve to 1, and the entity should be rejected as bad. So, as before we run our experiment, as is typical, what we would like to do is predict what's going to happen. In other words, we'd like to develop some expectations so that we can convince ourselves that it is behaving as expected. So, what should happen is the average number of adjustments should go down. The average number of adjustments should go down because we're not allowing any more entities that go beyond 3 adjustments to remain in the system. Similarly, the maximum number of adjustments, we've computed that using the population, by using the tally statistic coming from the sync node. This should equal 3 because we are recording that value at the good node. So we're recording the tally value here. If we're recording a tally value here, we would expect that value to be 4. And so let's run our experiment and see if that in fact occurs. And we see, based on our experiment, we get exactly what we expected. The maximum number of adjustments for entities that depart the sync 1 or the good sync is 3, and our average number of adjustments has been reduced. As I mentioned, you could also count, use a tally statistic here on the entities that enter the bad, and those should have an exact value of 4 because the only entities should enter here have a num adjust value of 4. And you should probably give that a try. Again, a 2-step process. You define the tally statistic, and then you record observations using the property here, tally statistics for the input node to bad. So I will leave that for you to do. So what we've done is we have now taken our decision point here and we've added a conditional element to our routing decision. And so the condition is based on this num adjustments. And so we have now combined it for a conditional and probabilistic routing to make a fairly complex decision using only the selection weights. Now, note that we also have some extra work in our system because we reject entities we reject entities once they've been adjusted more than 3 times. And so in fact we actually know that we're going to reject the entity somewhere along this link. So when the number of adjustments has a value of 3 along this link, we'd like to go ahead and reject that so it doesn't go through that 4th adjustment. In the model that we have an additional adjustment, and we did that just so we could demonstrate this using a conditional to do the routing. And so as one of the assignments that we'll see in the next video, I ask you to make an alternative model that will correct for that additional work. And so using selection weights and applying expressions to make them conditional and probabilistic is a very powerful feature and something that you want to explore further.